The first lecture will be held by Mr. Stijn Kragt. Mr. Stijn Kragt is the co-founder and CEO of Climate Technology. He founded the company after his PhD as smart coding materials at the Eindhoven University of Technology. And additionally, in the first years of his company, he was also postdoc researcher of architecture and engineering and technology at the Delft University of the Technology. And the lecture is Smart Photochromic Glass Films, the Evolution in Glass Performance. Stijn, the floor is yours.
Thank you very much. So while waiting for the slides, so my name is Stijn Kragt. I'm one of the founders and also the CEO of the startup Climate Technology. So Climate Technology, climate is a short for climate adaptive. So we are working on technologies that change themselves or adapt themselves by the environments surrounding them. And so in this case, we are talking about photochromic glass films, so changing themselves by sunlight in this case. So we know that glass can have a significant impact on the heat management of a building. So in the ideal case, in the summer situation, we would like to reject the solar heat to keep the indoor cool. And in the winter situation, we would like to have the solar heat getting through and keep the thermal radiation, this part, in to keep it nice and warm. And because we know that about 1/3 of the energy used in a building is used for space heating and cooling, then we can realize that with glass we can make a significant impact on the energy performance of a building. And in the last decades we have been doing a tremendous job as the glass industry in improving the U value of glazing, so working on this part, keeping that heat in winter. We've seen developments in low E coatings. We have seen also vacuum glazing these days, or even triple glazing with the thin glass in between from Corning that we saw yesterday. So because of this, we can better keep the heat in winter. And you also see the effects of this because in the past 10 years we have been able to decrease the heating energy use with about 4%, regardless that we are having more and more buildings. So this part here is decreasing. So we are on a good way, but still we have room to go because also we have to realize that still 81% of the buildings in Europe is equipped with low performance glazing, so uncoated double glazing or even single glazing. The average U value is 3.4, so that's less than uncoated double glazing. So we can still improve, and if we would upgrade all this glazing, we can still save almost 900 terawatt hours per year on energy use. So we have to keep pushing this. Keep doing this, but at the same time, we also see a different issue occurring, and that is because it's getting warmer and warmer in our climate. I mean, you can also notice from your own situation, for instance, in the Netherlands where I'm from, 25 years ago when I was a kid like this, the people used to ice skate to their work on the canals, but of course today that is not possible anymore because there's no frozen canals anymore. So probably you have your own story that relates to this as well. And because it's getting warmer and we are insulating our buildings better, so not only the glazing, also the roof and the walls of course, but because of this the energy demand for space cooling is increasing. So we've seen over the past years, 30 years, this tripled to about 3,500 terawatt hours per year. It is also expected to increase further to about 7,000 terawatt hours in the coming 25 years. And this is a global trend, but also, we'll move a little bit, also happening in Europe. As you see here, the numbers are increasing here, and also the expectations for air conditioning use are increasing. So as the glass industry, we I think we have the responsibility also to counteract this trend. And of course we can install low E coatings that can reject solar heat as well. So we can lower this energy need for cooling. But at the same time, these coatings do the same, have the same performance in winter. So they also reject the solar heat in winter, which then puts more stress on the heating demand. So it's not the ideal case. And therefore I think that the next evolution in glass performance would be to go to adaptive glazing that can switch or adapt by the environment. And that's why we are working on smart photochromic glass films. So these films, they are transparent in cloudy conditions, but as soon as the sunlight intensity increases, they get a tint automatically, and then also reject more solar heat. So this gives a situation that in summer, you can save more cooling energy use, while in winter you allow more of the heat coming in, and then prevent additional heating energy use in this period of the year. So this film is based on a coating that we can apply on a substrate carrier. So this is our first pilot production is 40 centimeter wide. But you see that it can get a homogeneous tint over this area at least. We can equip this film with an adhesive on the back, so that you can use it as an add-on film, for instance, to incorporate it inside an IGU on position 2, for instance, or on the outside on position 1. But we're also looking into ways to laminate the film in between glazing. So how this works is that over the day, when sunlight intensity increases, it gradually gets a darker tint. So you can see the difference here with the morning, and then at the highest point, and then if the sunlight intensity is decreasing, it gets back to its original state again. So you will also see that if there is a semi-cloudy day, it will get some intermediate state. So for instance, if you shine with different UV light intensities, you will end up with different visible light transmissions over there. Then from the tinted state, it goes back to the original state in about 3 hours. So already in about 1.5 hours, it's back to 70% visible light transmission. But the most special thing about this film is not the tint that you see, but especially the change in this part of the spectrum. So this is the visible part, which gives the tint, but this part is where the most solar heat is present. And because of this change, it is not only changing in the visible light transmission from 88 to 40%, but especially also in the solar heat gain coefficient, or G value, changing from 0.87 to 0.54, so 0.33 units difference. And this is very special if you compare it to other products that are already out there. For instance, photochromic films similar to us, which can change by light. They can do a very good job in changing visible light transmission, so the tint that you see. But in terms of solar heat gain coefficient change, this is about, the highest I could find was changing 0.09. So that's not so much on the energy efficiency between summer and winter seasons. In our case, this change of solar heat gain coefficient is 0.33. So then you get into the range of electrochromic glazing. I think we will hear more about this in the third lecture of this session about electrochromic. So in this case, you don't need the electronic wiring that is required for electrochromic. So as far as I know, this is the first smart glass product that can change the solar heat level or rejection level all by itself, at least for products that are already on the market. And of course, I know there is also research going on in this field other than this. And on top of that, the film is very transparent. So I brought a sample here. So it's quite boring because it's transparent and you can just see through. Just looks like a regular glass pane. I'm happy to show you later. You can have a closer look. I can also show you how to tint it. But in this transparent state, also the solar heat gain coefficient is very high. So if you compare to electrochromics that I could find on the internet, which are in the transparent state, the highest one I could find was at a solar heat gain coefficient of 0.51. So it is actually rejecting also solar heat in the transparent state, which is energetically not most favorable. And then, of course, it's a simple film that you can add on or laminate without the need of wiring. So also in terms of cost, it's very effective. So for this film we did, or this film we did an energy saving simulation. We designed this model of an office building together with the University of Delft. And then we installed different types of glazing. So we had just double clear glass as a reference, and then 2 types of low E-coated glass. One that has also a bit of solar heat rejection capabilities. And then we applied the film to these 2 types of low E-coated glazing. Then we looked at the energy consumption in the simulation for lighting, heating, and cooling. And we did this for different climates across Europe. So from southern Europe to Scandinavian climates, as we are having this conference today. And then you can see that you can save quite a lot of energy on cooling if you apply the film. So comparing this 3rd bar to the 2nd and the 5th to the 4th, you can see that you can reduce the cooling energy use. But as soon as you go to colder climates, you see that also the heating is getting apart in the energy profile. And the film induces a little bit on the heating energy use, although this effect is less when you compare it to permanent solar heat rejecting technologies. So the overall energy saving that you can get with the film is decreasing when you go to colder climates, till you are in Scandinavia where there's no energy benefit anymore. Although you can then still, of course, use it if you want the daylight comfort part that is also provided by this film. So if you put this graph in numbers, then we get to this table. So on this side, where we, if you would replace double glazing with smart E-coated glass number 2 in this simulation, we can save about 40% across all the climates in Europe. And of course, in the colder climates, this is more dominated by the increase in the enhancement of the U value. So if you just purely look at the effect of the film, then we can save, so retrofitting low E-coated glass, we can save up to 35% of energy in the warm climates in southern Europe, which then gradually decreases to lower percentages when you go to colder climates. And we thought of, okay, what could be the impact potentially for having this film across all the buildings in Europe? What would be the red point on the horizon? And then we have to consider these numbers. So still 81% of the European building glass can be upgraded with high performance glazing. And the energy used for space heating and cooling is about 3,387 terawatt hours per year. And then if you would change, I will stand here. If you would change the this 81% with low E-coated glass number 2 according to the simulation, we can save 32% of energy per building on average, which then translates to this number, 873 terawatt hours per year. So this is very close to the reference Glass for Europe gave in 2019. So it also says something about the reliability of this study. So this is our reference. Then, if we would do the same thing, so replacing this 81% with low E-coated glass number 2, but with the smart film, then we can save 41% on average, so the average of this number per building, which then translates to 1,122 terawatt hours per year. On top of that, you could say the other 19%, which is already low E-coated high-performance glazing, you can also retrofit and upgrade, give an upgrade with this film, which then on average can give average of this part 12% per building, which then translates to 80 terawatt hours per year saving. So in total, it adds up to a bit more than 1,200 terawatt hours per year, which you could save if the glass industry would adopt smart glazing, being it the one that I present or any other one. And that's why I think if you compare these numbers, if you want to enhance the energy performance in buildings, then the evolution in this field would be to go to adaptive technologies. On top, of course, of a good insulating value. So the combination is the holy grail. So you might wonder why this is not applied everywhere already. Well, the reason is simple, because we're still developing it. So far, we have shown that we can have a scalable, smart photochromic glass film with a large solar and visible light modulation and high energy saving potential. Currently, we are improving this product on the lifetime and also the switching speed, especially when we incorporate it inside an IGU. We hope to have done this by the end of the year. And then after this, we aim for pilot studies. So we have already found partners to do this. So these are the partners, and we also, financed also by the Dutch government. So thanks also to these partners and finances, of course. And with these pilots, we hope to validate the outdoor operation of the film and the energy saving potential and comfort in the actual real world. So hopefully next time at GPD I can tell you more about these developments. In the meantime, we are also looking for collaborations with the glass industry, but also with architects to see what the impact can be, and with the glass industry to see how we can process this film into an IGU, or inside an IGU. So yeah, feel free to reach out to me. You can also find me on LinkedIn or send me an email if you like, or just ask your questions now, right away. So thank you.